Hello everyone, here's another Physics 30 example set. This time we're in Unit 4 EMR, and this is Lesson 2, which is to do with the speed of light. We would have reviewed all of the different, the beautiful story of how the speed of light was slowly revealed through scientific experiment and inquiry. But today we have an example question from the Michelson experiment. So this, of course, is the famous sided mirror. In this case we're looking at an 8-sided mirror. Of course there could be any number of sides, and what essentially they did, or he did, was he had a light source and it was shone at a spinning mirror, of course, and the light reflected off one of the sides of the mirror, off another fixed mirror at some set distance, back again, such that it would perfectly reflect into the observer's eyes. So of course, if this mirror was not spinning, you would be able to see the light source. If the mirror starts to spin slowly, that means that the light, as the light is traveling from here to here and back again, the mirror has turned ever so slightly, and therefore the angles are not going to line up and you will not see the light. But if you keep increasing the speed of rotation, the angular speed, eventually you can get to a point where it completes 1/8 of a turn, just in time for the light to then reflect off the mirror and into your eye. So for example, this side of the mirror, the side that I've just drawn red, is in this position when the light is striking this side of the mirror. It then travels all this way, all the way to here, and all the way back again. In this case, a combined distance of 35.5 kilometers times 2, because it's there and back. And in that time, the mirror will have rotated 1/8 of a turn, which means that this side of the mirror that we initially indicated to being red actually is now in this location here, and then you can see the light perfectly. And so, you know, if you've got your spinning mirror set up just right, you know that it's rotated 1/8 of a turn in the time it's taken light to go that way, well, all the way to the fixed mirror and back again. So that's the idea. In this example question, we have a particular situation whereby, let's just get rid of these, whereby we are told the rotation is 36,000 revolutions per minute. Yep, you read that correctly. These mirrors are spinning pretty fast. They have to, because of course we're dealing with the speed of light. It's very fast. So let's just turn this into a number that a unit that we can deal with, because 36,000 revolutions per minute is not in SI units. We want this to be in seconds, because almost all of the things we do in physics are in seconds. So we're going to just multiply this out. This is in revolutions. Well, actually, I'm just going to, revolutions. I'll put revs over minutes. So we're just going to unit cancel this out, because I want it in revolutions per second. So I'm going to make sure my minutes cancel. So I'm going to put them there so that the unit cancels, and then seconds there. So I'm going to say that 1 minute is 60 seconds. So of course I have to divide 36,000 by 60, and that gives me 600 revolutions per second, in other words, hertz. Okay, so this is good. This is what I want to deal with, because I'm in seconds, and that's going to match up with my meters per second, which is of course my SI unit. Okay, we're now told that the speed value is given as well. So we have a measurement for the speed. It's not quite as much as the speed of light that we know to be, but we're going to write that down. So we're going to say that C, in this case, the measured value for C was only 2.7 times 10 to the 8 meters per second. Why would it be so much less? Well, measuring the speed of light is so fast that the tiniest amount of error in your experiment is going to give you quite a bit of error in your calculation. So this value would have just come from experimental error. Okay, there's our speed, which we're going to try and verify. But what we're asked to do is find out how what's the distance? Well, how far away is it? So we should be used to thinking about the Michelson or the spinning mirror type of experiments as giving us value for C that is essentially, well, it's going to be essentially distance over time, but in the spinning mirror speed of light experiment, the distance is going to be twice because it has to go there and back, so we're going to say 2d, and then the time, well, this is going to be the time it takes to do one fraction of the turn. Well, in rotating objects, the turn is called the period, and of course we only want a fraction of the mirror. Well, how much of a fraction? Well, however many sides it has, so this is going to be 1/8 of the period. Okay, so this is a formula we're used to seeing. Now, we also know that the, let's put it up here, that the period is the inverse of the frequency. So I could rather than putting period, I could put frequency in the top row of my equation here. So I could say 2d, I'll keep the 1/8 there for now, 2df. Okay, because f is the inverse, so it just comes up to the top part of my equation. And then, of course, because I've got 1/8, I can just say 8. Okay, so this is a formula we want to get used to using, 2dnf. Okay, that's a pretty good one to memorize, but obviously it's useful just working it through, essentially coming from the speed equation. Speed is just distance over time. Okay, so there's our equation. We know the frequency, so this is my f. Frequency is 600 revolutions per second, or 600 hertz. I know the speed. What I'm trying to find out is the distance. So let's just rearrange this. I've got 2d, and that's equal to the c value. And now I'm going to divide by nf, and then of course I can divide by 2nf just to get it on its own. So the distance, the individual distance between the mirror, which is what we're asked to find, not the total distance, it's determined the distance between the mirrors, so just one way, is going to be the speed value that was given divided by the number of sides on the mirror, which is 8, divided by the n, multiplied by the f times 2. If we put that in, I'm going to get those values there, and if you put that into your calculator, you're going to get 2.8125, a few other digits that we're going to ignore, times 10 to the 4. So that means, of course, actually let's go 28 kilometers. Okay, and that's 2 significant digits, which matches my question. 28 kilometers. Now, just to double check, I'm just going to do my units. Yeah, the seconds here are going to cancel out, and we're left with meters. Meters per revolution. Well, per fraction of a revolution, we can kind of ignore that as well. So meters, and that's good because we're finding a distance. So there we have it, 28 kilometers.